So, good morning to all. In the previous class, we have discussed about the boost buck converter. So, we have concluded that in the buck converter, the output voltage is always less than the input voltage. In this lecture, we will discuss about the boost converter. So, as the name indicates that boost converter, the output voltage is always greater than the input voltage. So, boost converter is a DC-DC converter where the output voltage is always greater than the source voltage. It's sometimes called as the step-up converter, just like the buck converter is step-down converter. It's a step-up converter because the output voltage is always greater than the source voltage. So this is the very basic diagram of the boost converter. It is very similar to the buck converter. Only difference is we have changed the position of the inductor and the diode. So here we have used two semiconductor devices. One is diode and one is BJT. Transistor, MOSFET and MOSFET. So you know the working of the N MOSFET. There are three terminals. One is gate. This one is the gate, source and drain. Gate, source and drain. Whenever your gate signal is high, whenever you give a high gate signal, this device behaves like a short circuit, means it's on. Whenever your gate signal is low, this is behaves like a open circuit or insulator. Okay, this is your diode, power diode. This is capacitor, this is load, and this one is your inductor. Your input is applied to this side. Okay, and we are getting the output towards the load. Okay, this is the very basic circuit diagram of the boost converter. So let us now understand the working operation of this boost converter. So there are two modes of the operation in the boost converter. Then in mode one, what is happening? This your MOSFET is turned on, means in mode 1 your transistor is on, M1 is on, M1 is on means it behaves like a short circuit. So we are putting short circuit across this M1 here. It's a short circuit. So your output voltage across this is zero because this input side is totally disconnected from the output side. Okay, so this is short circuited, the output voltage is zero. All the energy is stored in the inductor. This is minus, this is plus. So this is your T on period. During your T on period, the current is flowing in this part only. Okay, the output is zero. Inductor is storing the energy during the cycle T1. So mode 1 begins when the transistor M1 is switched on at time is equal to 0 instant. The input current rises and flows through the inductor and transistor M1. Inductor is gets charge up to the value of is storing the energy. Inductor is storing the energy. This one is plus, this one is minus terminal. In next cycle M2 mode second. In mode second, your gate pulse is low. Gate pulse is low means your transistor is off. Transistor is off means it behaves like an open circuit. So we have put a open circuit across here. Okay, here is the open circuit. Now in this case, your current will flow throughout the circuit. This through inductor, diode, capacitor, and the load. Your output will get the output. So the output voltage across the load is always greater than to the input voltage. Why? Because input voltage is Vs. In the first cycle, your inductor is stored the energy across this. So VL, inductor is charged up to the value of VL. So your output voltage Vout is always Vs plus VL. So Vs plus VL means your output is always higher than the input. Okay, in mode second. So this is the basic working of your boost converter. Mode 1 and mode 2. Mode 1, your MOSFET is on. Mode 2, MOSFET is off. Mode 1, MOSFET is on. So we have short circuit T on period. This is T off period. T on period output voltage is 0. T off period output voltage is always greater than the input voltage because output voltage is getting the value of Vs plus of VL. So let us do some mathematics. So just forget this. We know that the VL, the voltage across the inductor, is given by the L di by dt. Okay, so we can write here I equals to di is equal to V by L. V by L into T. Okay, V by L, this I di equals to V upon L into T, V into T. Okay, so for a constant rectangular pulse, current I is given by, just eliminate the differential word. I is given by the Vt by L plus of I naught. Very simple mathematics. So when your transistor is on, your current I of Pk is given by the input voltage minus drop across the transistor. Its drop is almost negligible. The drop across the transistor is almost zero. What is written? Just like in this circuit, what is happening? Your this circuit, when you're on, then when your transistor is on, that means your voltage across this is Vs, and difference in this, how much is drop. Ideally it is short circuited, but in practical there is a drop, very minute drop, but practically it exists, very minute drop exists. So we have written this Vn minus of V voltage drop across the transistor multiplied by T is the T on period, because we are calculating during the on time. If we are calculating during the off time, then it would be T off. So V in minus V transistor into T on upon L plus of I naught. So can be written as change in current is just here IPK minus of I naught, that is the change in differential current. V in minus V transistor drop into T on upon L. And when your transistor is off during the next half cycle, your I naught is given by the IPK minus of V out, output voltage. We are getting the output voltage is getting the Vs plus of VL, V out minus of V in plus of VD, voltage drop across the your diode, and multiply by T off during the off period upon L. So after solving this, you will get the your VD is the voltage drop across the diode DM, and T is the voltage drop across the transistor M1. So just equate the both delta I. By equating the both delta I, you will get this. And after solving this, you are getting this value. V out is equal to V minus transistor drop into D upon 1 minus G minus VD. You can easily compute this. So neglecting the voltage drop across the diode and the transistor, because we have assumed that ideally the diode voltage drop across the semiconductor devices, whenever they are on, ideally it should be zero. So when neglecting all these terms, we are getting a very simple V out upon V in is equal to 1 upon 1 minus D, or V out is equal to V in upon 1 minus D. So it is clear that the output voltage is related directly to the duty cycle. So here we can see that the output voltage is V in upon 1 minus D. 1 minus D something 1 V in upon 1 minus D. So a V output voltage is always greater than to the input voltage. So here is a boost operation is performing. So we are getting the output voltage boosted. We are getting the boosted output voltage with respect to the input voltage. So again, we can write this V out upon V in is equal to 1 upon 1 minus D, as we said earlier. The application shows that the output voltage is always higher than the input voltage as duty cycle goes to 0 to 1, and it increases with D theoretically to infinity as D approaches to 1. This is why the converter is sometimes referred as the step up converter. It's just the same basic statement that we had earlier talked about. So rearranging the duty in terms of the duty cycle, D is equal to 1 minus Vi upon V naught. So this is the output waveforms that of this boost converter. So here is a pulse, input pulse, when on period, off period, on period, off period. On period is going to D into T, as we talked about in the buck converter. Buck converter derivation, D into T and 1 minus D into TS. Okay, TS is the time period. So this is your inductor current. Inductor current during the on period. During the on period, inductor is getting the value from input and getting charge. During the off period, inductor get discharge. Inductor get discharge. Okay. Similarly, on period, charge, discharge. Your output voltage is always greater than to the V input plus of VL. So this is your VL, this is your VL, and this is your input voltage. Okay. So your output voltage is always greater than the V output voltage. V out is equal to VL plus of VS. So that is why it's a high pulse. It's a maximum pulse from this to this. Okay, output voltage is higher than the input voltage. What about your inductor current? Inductor current is I minimum. Whenever your inductor and the T on period, inductor gets charges, and inductor stores the energy. So your inductor is storing the energy. This gives to high, and whenever your off cycle, the inductor releases its energy. So it's like this, and like this. This is I minimum, and this is I maximum. What about your diode current? In diode current, during the first half cycle, during the on period, the circuit is totally isolated from the input side. So diode current should be zero. So there will be no diode current. And whenever there is a off cycle, then we will get some sort of diode current. So this is the waveform of the diode. So this is the basic waveform for the boost converter in continuous mode. So what are the advantage with this boost converter? So it's a one switch, high efficiency, unidirectional output current, provides one polarity output voltage, low cost, it is easy to analyze, easy to understand, and it's a very simple circuit, just like the boost converter, just like the buck converter. And what are the exam disadvantages? Not suitable for the high power conversion, low amount of the DC setup, non-isolated as SMPS. SMPS stands for the switchboard power supply. So just revise the duty ratio. What was the duty ratio? That we already talked about T on upon T. Simple T of is equal to 1 minus D upon T. Just the previous thing. Just recap. And voltage across the inductor is V out upon V is equal to D upon 1 minus T. Very easy. Previously we have done this. So this is the duty ratio versus voltage graph. So in case of the buck converter. So buck converter, the voltage swings from 0 to 1 volt and duty ratio is 0 to 1. In case of the boost converter, the output voltage is higher than that, so 1 to 3 volt. And buck boost converter is another kind of converter which is not in your syllabus, but it's something like this. This is the duty ratio versus voltage graph. So what are the application of the boost converter that is used in many industrial applications such as the subway cars, trolley buses, battery operated vehicles, battery charging, etc. To provide the smooth control of an output, high efficiency, fast response and regeneration, to provide the efficient control on DC motor operation, to provide a long life and less maintenance due to the absence of the moving part. Okay, thank you. Just I will summarize once again. Today we learned about the boost converter. Just like the buck converter, in boost converter, it's just opposite to the buck converter. In buck converter, what was happening? The output voltage is always less than to the input voltage. In boost converter, the output voltage is always just opposite, higher than the input voltage. So it's a step up. So very basic circuit. We have we have changed the positions of the inductor and the diode, and we have used a MOSFET. In MOSFET, the gate pulse is high, the MOSFET is on, gate pulse is low, the MOSFET device is off. So there will be two modes of the operation. In mode first, what is happening? In mode first, your MOSFET is on, means your gate pulse is high, your output is completely disconnected from the input side. So your output will get the value of 0, V out is equal to 0 during the T on period. And during the T off period, then your gate pulse is low, your MOSFET is off, it's isolated, so your current is going through the inductor and diode and capacitor and all along this, and you will get a output voltage is equal to the V out is equal to V input plus V of L. V of L, why V of L? Because in the first half cycle, in the during the this mode 1 operation, your inductor is getting charged to the value of VL. So output voltage is we are getting the output voltage higher than the input voltage. That is how the boost conversion in operation is performed. Simple mathematics, we have done simple mathematics, and after solving that, we get the output voltage is equal to V in upon 1 minus D1. D is the duty cycle. So these were the waveforms. Okay. Thank you guys. Thank you for your patience. Do learn. Thank you.